Hey guys, Mr. Martin with a video for basic derivative rules. In this video, we will cover the derivative of a constant, the general power rule, the derivative of sine and cosine, and rewriting rational functions so that they have negative exponents. And we will also discuss what a horizontal tangent is. So again, we're covering constant derivatives, the general power rule, the derivative of sine and cosine, and when we have negative exponents. So I'm working examples from your textbook. This can be found page 115 through 119. I'm pretty sure I don't get to page 119. I just copy some examples that kind of illustrate the basic properties that we're covering. So when we're doing just the general power rule, all we're doing is taking this exponent, multiplying it to the front, and subtracting 1 from the exponent. If there's a number already in the front, we multiply that previous exponent and that number. The example that we have is if we have 3x to the 4th, then we multiply the 4 to the front, and that's multiplied by 3, and we subtract 1 from this exponent, and so we get 12x cubed. We're also always applying the sum and difference rule, meaning that if we add a bunch of different terms to find the derivative, we just add and subtract the derivatives of each term. So in the example in the notes, we have tangent x plus the square root of x minus 5x. Now the square root of x can be rewritten as x to the 1/2. And so the derivative of tangent is secant squared plus the derivative of x to the 1/2, which is 1 over 2x to the negative 1/2. And then the derivative of negative 5x is negative 5. So when we're doing our examples, we're applying all of these rules, and it's very simple to follow. So for number 18, all of these we're just finding the derivative. So the first derivative is we multiply 3 times 2. We get 6x squared minus, we multiply 2 to the front, we get 2x to the first. And then the derivative of a line is just the slope, so that's just going to be plus 3. And that's our derivative. For number 19, we're going to have y prime equals, so this is where we should remember that pi over 2 is a constant, not a variable. So anytime we have a constant multiplied by a function, we just take the derivative of the function and keep the constant. The derivative of cosine is negative sine, so we're going to have pi over 2 times negative sine theta. And then the derivative of sine is cosine. So we don't have to actually take this step. We could just multiply by a negative and put it in the front initially, so we get negative pi over 2 sine theta minus cosine theta as a final answer. And then for number 24, I wrote it backwards, but it's the same problem. So the first thing is we have 5 over 2x, and the quantity is cubed. So we should rewrite this as f of x equals 5 over 8x to the 3rd plus 2 cosine x. And we should further rewrite this so that the x is in the top. So one thing we're going to find out when we're doing derivatives and integrals is that unless we're doing some weird formula, we can't ever do anything with the x in the bottom. So we're going to make this 5 over 8, and we're going to have x to the negative 3 plus 2 cosine x. And again, this is a rewrite step. It is not the derivative. The derivative, and this is why we should label our functions, is so that we know what function we're actually in. The derivative is going to be negative 3 times 5/8. That's going to be negative 15 over 8. And then we're going to get x to the, and when we're subtracting from a negative exponent, we have to be sure that we're actually subtracting, and we should get negative 4. And then the derivative of cosine is negative sine, so we're going to have negative 2 sine x. Now, if we were looking for a proper final answer, this would be negative 15 over 8x to the 4th minus 2 sine x. And so again, I want to emphasize that the x is what we bring up, not the 8. And in this case, if we brought up anything, it would have been the 2x. We could have brought the 2x up here because the whole thing is to the third power. But here, only the x is cubed, so only the x moves up and gets a negative exponent. All right, for number 45. So we've already covered the product and the quotient rule. So in class, I said you should only use the quotient rule when entirely necessary. Example 45 is a case where it's not entirely necessary because we have a long numerator over a denominator that contains a single term. So instead of doing the quotient rule, we can rewrite this where we have x cubed over x squared minus 3x squared over x squared. And since we're just going to have 4 over x squared, we'll make that 4x to the negative 2 power. So this obviously simplifies to be x minus 3 plus 4x to the negative 2. And again, this is still a rewrite step. We've not found the derivative. The actual derivative is going to equal, the derivative of x is 1. The derivative of any constant is 0. So then we're going to have 4 times negative 2 is going to be negative 8x. And again, the exponent goes down by 1, so negative 3. And in a rewrite step, we would have 1 minus 8 over x to the third power. So that's our final answer. So again, if you have a whole numerator over a single term in the denominator, you can always put each term in the numerator over the denominator. That's different if we flip this around where we have x squared over x cubed minus 3x squared plus 4. This requires the quotient rule. This expression requires the quotient rule. This one does not because we can simplify. We can't say x squared over x cubed minus x squared over 3x squared plus x squared over 4. We can't do that. So these two things not equal. These are equal. These two not equal. Requires quotient rule, does not require quotient rule. All right, so moving ahead in our examples. So we come across this cube root of x and the fifth root of x. In case that's not clear, I can do some better handwriting. This is the cube root of x plus the fifth root of x. So anytime we have the nth root of x to the k power, that's going to be x to the k over n as an exponent. So anytime we see radicals, immediately we want to maybe rewrite the problem. If you can internalize and remember, it's not necessary, but I would just recommend writing it down so you can see it. So we have x to the 1/3 plus x to the 1/5. And so now when we find the derivative, we get 1/3 x. 1/3 minus 1 is negative 2/3. A handy trick, if you are wondering, you can always do numerator minus the denominator, and that's what the new numerator would be, and the denominator never changes. So we're gonna have then plus 1/5 x. 1 minus 5 is negative 4, and we just leave that as negative 4/5. So if we are doing a rewrite step, we can make this 1/3 cube root of x squared plus 1/5 fifth root of x to the 4th, because this would be x to the 2/3 and that would be x to the 4/5. Now, we shouldn't use this actually. We should actually just leave it as 1/3 x to the 2/3 plus 1/5 x to the 4/5. we don't want to use this because in calculus, this is more useful. Having rational exponents is more useful than having radicals. So don't do this. It's not incorrect. It's just this is preferable. So for number 58, we are writing the equation of a tangent line. So to do the equation of a tangent line, we need a couple of things. Tangent line requirements. So we only need two things. We need one, a point on the line, and two, we need the slope, which is the derivative at the point, the value of the derivative at the point. So I don't actually give us a point here. So let's say we want to do this at x equals -3. So the first thing is we need a point on the line. So when we substitute in -3 for x, so y when x is -3 is going to equal -3 squared plus 2 times -3 times -3 plus 1. So that's 9 minus 6, which is 3 times -2, which is -6. So the point on the line, the point on this line is -2, -6. So the next thing we need is the derivative. So let's bring this function down. We're gonna do we're gonna multiply this out. So again, some problems do not require the product rule and some do not require the quotient rule. You should really only do the product rule when you have exponents that make expanding a polynomial difficult, or you have like a sine or cosine or some transcendental function multiplied by an algebraic function like x squared or x cubed or something. So when we have this, we can just FOIL or double distribute and rewrite this as y equals x squared times x is going to give us x cubed. X squared times 1 is, that's going to be plus x squared, but then 2x times x is 2x squared, so total we get plus 3x squared, and then 2x times 1 is plus 2x. Let me check my math on this because I have a habit of making mistakes. This point is -3, -6, so not -2, -6. This should be -3, -6. And so when we substitute in -3, we're going to get -27 plus 27 minus 6. So that is -6. And so now when we're finding the slope, we need the derivative. So that's going to give us 3x squared plus 6x plus 2. And the derivative evaluated at -3 is, it's going to be 27 minus 18 plus 2, which is 11. So the equation of the tangent line, we're generally going to do in point slope form. So that's going to give us y minus -6 equals the slope, which is 11 times x minus -3, or y plus 6 equals 11 times x plus 3. So if we had to write this in slope-intercept form, we'd have y equals 11x. That's going to be 11 times 3 is 33, minus 6 is going to be plus 27. So either of these answers is correct. Point slope form, slope intercept form. So again, to write the equation of a tangent line, you always need the point on the line and the slope, which is just the derivative at that point. And so for the last one, we are finding the horizontal tangent. So the horizontal tangent for a the horizontal tangent for an equation is where is the slope equal to 0, which is the same as asking where is the derivative equal to 0. So we need to find the derivative and set it equal to 0. So we're going to get y prime equals, now the square root of 3 is not a variable, it's a constant. So the square root of 3x, its derivative is just square root 3, and the derivative of 2 cosine is negative 2 sine x. And so again, horizontal tangent implies the derivative equals 0. So 0 equals root 3 minus 2 sine x, and we get 2 sine x equals the square root of 3, and the sine of x is equal to the square root of 3 over 2. So if we're solving this properly, we would introduce a sine inverse on both sides. So this gets us an x. And remember, inverse sine is properly defined on the interval negative pi over 2 to positive pi over 2 inclusive. So sine is square root 3 over 2 at pi over 3 or 60 degrees, whichever you prefer. Now, in calculus, we're only going to use radians. So pi over 3 is one of the answers. But notice that we have an interval of 0 to 2 pi. So if we don't remember, sine is positive when the y value is positive. So sine is positive in quadrant 1, and sine is positive in quadrant 2. So the other quadrant 2 angle is, if you know the angle in quadrant 1, you subtract this angle from pi, and that would also get us 2 pi over 3, also known as 120 degrees. All right, so that concludes this video over basic derivative rules. Again, all I did was we worked 115 through 119. We did the general power rule. We did the derivatives of sine and cosine. We rewrote negative exponents. We simplified rational functions into a string of just polynomial terms. And we rewrote radicals so that we had rational exponents. And lastly, we found the equation of a tangent line by writing the information that we needed. We also learned that we can sometimes multiply things out without having to do the product rule. And lastly, we determined that a horizontal tangent is where the derivative equals 0, and we have a process for that. So that concludes this video, and if you need more practice, please talk to me in class.